Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to radioactivity and nuclear reactions in the chapters of radioactivity and simulated nuclear reactions, fission and fusion. This exercise was a previous one on the terminal LH and SE exams, 2021 second session, exercise number 2. Now the title of this exercise is the age of the lunar rocks. Now, the aim of this exercise is to determine the age of the lunar rocks brought back by the Apollo 11 astronauts. A sample A of this rock is collected. This sample contains certain quantities of the radioactive isotope potassium-40, and this is the symbol of this nucleus, as well as the product obtained by its disintegration, which is argon-40, and this is the symbol. Now, let's start by number 1. They are telling us to define radioactivity, so this is straightforward, which is the definition. Then let me say radioactivity. So it is a spontaneous nuclear transformation during which an unstable parent nucleus disintegrates and gives a daughter nucleus in addition to the emission of radiation. Then this is basically the definition of the radioactivity. Now they are telling us to indicate the composition, the number of protons and the number of neutrons of potassium-40. So this is the nucleus potassium-40, and we know that the nucleus, its composition consists of the protons and the neutrons. Then now the symbol of the potassium-40 is given by that. Then let's recall that this is the mass number and this is the atomic number. Then let me say that Z, which is equal to the number of protons and in this case, so Z is 19 and this is given by 19. So always remember that the nucleus is being represented by XAZ, in which Z represents the atomic number and A is the mass number. Now regarding the number of neutrons, which is given by N, remember that N is given by A minus Z. Then we need to subtract the number of nucleons, which is A, minus the number of protons. Then let me say that the number of neutrons, so then N represents the number of neutrons, and this is equal to A minus Z, and we know that in this case A is given by 40 and Z is given by 19. Then in this case the value of N is given by 21. Then this is it for number 2. Now in number 3 they are telling us one of the decay equations of potassium-40 is given by that. They are asking us to calculate the values of Z and A. Then here, so Z and A here are represented in this decay. So for sure A and Z are calculated using certain laws. Then let's start by the law of conservation of the mass number. So remember that in any decay, the upper number must be always conserved. So the one before must be equal to the one after. So here, for example, let me say according to law of conservation of mass number so then initially it's given by 40 and this must be equal to 40 plus a, and we are searching for the value of a. Then in this case a is given by 40 minus 40, which is equal to 0. Then the mass number of this particle is given by 0. Now we need to determine the value of z, and this can be done in the same way, but now according to the conservation of the atomic number. Then according to law of conservation of the atomic number. Then initially it's given by 19, and this must be equal for sure to 18 plus z. And we are searching for the value of z. In this case, z is given by 19 minus 18, which is equal to 1. Let me make some space. Now in number 4, they are asking us to indicate the name and the symbol of the emitted particle. So now x, a, z, let's replace the values of a and z, is given by x, 0, 1. Then the atomic number is given by 1, and the mass number is given by 0, so this is a positron. Then the name is a positron, and its symbol is given by, so it's given by E, 0 plus 1. Now in number 5, 5.1, or let me say, the half-life period of potassium-40 is given by capital T, which is 1.25 times 10 to the power 9 years. Then let me write it here. Now what does the period represent? The period represents the time taken for this amount to be reduced to its half. Then in 5.1, eventually they are asking us to define the half-life. So let me write it down. So this is straightforward, just a definition. Then let me write the half-life. For sure, here we are talking about the half-life of the radioactive substance. Then it is the radioactive period T. Which is given by the half-life of a radioactive nuclide. Which is, so let me say, is the time interval after which the mass or half the number of radionuclide disintegrates. Now in 5.2, they are telling us that given that M1 is equal to 1 over 8 M0, where M1 is the mass of potassium-40 found in the sample A, recall that the sample A is the one being extracted from brought back by the Apollo. Now, and M0 is the initial mass of potassium-40 present in the sample A when it's found at T0 is equal to 0. Now, they're asking us to determine the age of the sample. Then the age of the sample is denoted by T. And we know that in order to determine T, first we need to determine N, which is given by the ratio over T over the half period. And this can be simply done by referring to this equality. Then we know that M1 is equal to 1 over 8 M0. Then we need to rearrange this equation in the following form. M1 divided by M0 is equal to 1 over 8. And this is simply done by the cross multiply. Then here we have that M1 divided by M0 is equal to 1 over 8. And this is eventually must be equal to 1 over 2 to the power n. Then in this case, one can deduce that because we have the same numerator, that A is equal to 2 power n, then 2 power n is equal to 8. And we know that the value of n in this case must be equal to 3, then n is equal to 3. But we are not searching for the value of n, actually we are searching for the age of the symbol, which is the time. We know that n is equal to t, the time, or the age divided by the half-life, and we are searching for t. Now, if we rearrange the following equation, then t is gonna be n multiplied by capital T. Now here we have calculated and we have found that the value of n is given by 3. And it's given that the half-life of this sample is given by 1.25 times 10 to the power 9 years. Now plugging this expression on the calculator, then this is equal to 3.84 times 10 to the power 9. Since this time is expressed in years, then this time will be expressed in years. So that's it for me in this video, guys.